way of using set timeout, which is completely unnecessary for what I've shown you so far, but it'll come in necessary later. And the slide's actually a little botched, but it's interesting. Right at the very top, you have this function called generate queries. You test to see if it's the last query. If it isn't, you call set timeout, generate queries again, which is going to recall this function a second later, just as a way to time it out a little bit. Then it's going to go down, create the anchor element, then set the href to it to the next necessary LLD, the next piece of data you want to exfiltrate. Then you set it to the domain you control, and then give it any random resource. It really doesn't matter. Then when you append it to the body, that's going to send out your DNS request. But then just kind of remember this technique because we're going to come back to it later where it becomes more necessary. Now, what if they have prefetching disabled? You're still actually able to separate the DNS from the HTTP here without exploiting prefetching. You have to think what happens when you set the source of a dynamically created object. Let's look at images now instead of anchor elements. The second you set the source, it's going to send out the DNS request, and then it's going to follow it up with an HTTP request. But the HTTP request won't be made until the DNS response is received. Well, the first thing you can do is just return NX domain from the name server, or from the domain server. And when you do that, it doesn't have a domain it doesn't have an IP address to send the request to, so it just can't do it. An NX domain reply basically means that doesn't exist. We have no idea. So the browser will be unable to make the HTTP request. One problem is that a lot of people, once again, going into the behavioral analysis, may detect that there's hundreds of NX domain replies going through the system, and that may throw some flags. So what you can actually do instead of that is black hole the requests until they time out on the server side. And when you do this, the NIDs will not see the NX domain replies. However, the problem with this is that the JavaScript will halt for long periods of time when this happens. It'll actually sit there and wait for that DNS request to come back before it'll continue on. So you got to find a way to mitigate that. Now, once again, this takes us back to that little technique I was showing earlier with the set timeout. Now we've changed from creating an anchor element down at the bottom to an image element. And once again, when we set image.source here, it's going to send out the DNS query, but then it's going to halt. Well, in this case, it's not going to matter because it's going to call this generate queries again. I actually put generate next query there, but it's going to call generate queries again, and it's still going to continue down and generate the next LLD at the bottom. And you're going to go ahead and send out your next packet. And what you're going to do is you're going to build a little queue of halted threads until they time out in the end. Now, for bidirectional communication, the first technique you can use is timing channels. You're able to use a conditional test to determine whether or not a packet should be sent for a current interval, or once again, you can replace in that set timeout call where I had set timeout every second, you can replace that second with a function that generates how long a timeout should be to represent some symbol that you're wanting to send out. And you can use that for communication. And once again, for the reply back from the server, you can just calculate how long that reply took and then use that to determine what symbol was sent back from the server. And then this isn't going to give you a lot of bandwidth, but it's easily going to give you enough for things like reliability and sequencing and things like that. And then you're actually able to create a storage channel as well by alternating back and forth between NX domain responses and timing out. What you can actually do is right after setting the image.source in this case, where it's going to time out whenever you black hole, you can have a data structure afterwards that actually keeps a binary response from the server. Anytime NX domain is received, it's going to fall through and actually set that sequence number to true in the data structure after it. Whereas anytime it's black holed, it's going to halt at image.source, and it's not going to come through, and it's still going to be the array is still going to be false at that point. So you actually build a binary storage channel response in that way. And one thing I thought about, and I was surprised I'd never actually heard of this before, but I thought it was kind of funny. One thing you can do just to play around with cybersecurity. I've never seen this out in the wild or anything, but I thought it was interesting. It's actually very easy, and just with a couple lines of code, you're able to create JavaScript that'll randomly generate these really long subdomains, and then you can actually use whatever domain you want. You don't have to control it. But if you just create these very long subdomains of random nonsense data, you don't actually have a file or anything. You can throw this on any website or execute it in your own browser, and it's going to make that computer look like it has some sort of data exfiltration or DNS tunnel scenario coming out of it, when in actuality it's just some harmless JavaScript running in the background. But it's going to look very malicious, and they may scramble and try to figure out what's going on there. But I thought it was interesting how easy it would be to actually mimic a DNS tunnel or basically an owned box without actually doing anything to it. Now, DNS tunnel detection, I'm going to talk about this a little bit, character frequency analysis, and then I'll get into PSUDP. Lengthy subdomains is easily the easiest way to detect it. All of the DNS tunnels I talked about earlier and all the most popular ones out there, they all have very long subdomains because they're trying to squeeze as much data as possible into every one of the packets. And that's really just an obvious telling sign in that case, and then also large amounts of traffic. Both of these are really the low-hanging fruit, and they're the easiest way to detect all sorts of DNS tunnels out there. And another actual very good method is doing statistical analysis on the resource record types. Like I mentioned earlier on responses, a lot of the tunnels will use null or text and resource record types. And those really aren't seen that often to most systems in a network. There are a couple that are going to be sending out a significant amount of traffic with those. A lot of blacklists and things like that use them. But for the most part, most systems should not be using those types of resource records much. So if you see a lot of them, it's really a red flag that there's something going on there. But this is really an underused method. I'm surprised there aren't more tools out there that do this. Neural networks were actually used by Jared Hind. He talked about this at DEF CON 17 last year. And he actually had really well-chosen training material using things like lengthy subdomains. But I'm not real excited about the idea of using neural networks. I think just some custom thresholds and algorithms would probably do the job just as well. But his idea for the training material kind of set me on my path on what I started studying. And then finally, you can do n-gram frequency analysis of subdomains. And I created a tool and presented previously called ngviz. I'm going to show you a couple slides on that. Basically, the idea behind character frequency analysis is the same as Hangman. There are certain characters that are going to show up more often than others. This was primarily brought about by Zipif and Shannon. Shannon was popular for calculating the entropy of the English language. Now, domains aren't necessarily a language themselves, and I wasn't even sure if they'd particularly match up to English incredibly well, since there are a lot of different random domains out there. I mean, you have like the cartoon site XKCD. You have a lot of random things. I wasn't sure how well that would work. So what I did was I actually mined the million most popular domain names of 2009 and ran n-gram frequency analysis on that. For n-gram, I mean unigrams, bigrams, and trigrams, groupings of 1, 2, and 3 characters. And the results I got were actually absolutely amazing. This is a graph for unigrams for one character showing the frequency of how often the character showed up compared to its rank. By rank, I mean the top most showing up character, the second most. And then over on the right, you can see a little graph that shows you with domain or English on the left and domains on the right, how well the character ranks matched up. And you can see it's actually amazingly accurate. So I started thinking this may be possible. So what I created was this tool called ngviz. And what this does is it allows you to load up a fingerprint of your typical network traffic. What you do is you'll record your network traffic for however long you'd like, and you load this up into the system as the fingerprint of what the traffic should look like going through the network. And then what you do is at any other point, you take any captured traffic and throw it into the system. You can either separate the traffic out to analyze each IP address separately or each domain separately, in case you have several IP addresses all using the same domain for something. And it'll separate each of them out and analyze them separately, and then give a percentage match to the fingerprint of what legitimate traffic should look like for character frequencies. And what this actually came out with some pretty amazing results. Here you can see there was about 20 simulated users here, and what they were doing was actually just going to popular websites out there and crawling them, taking every domain and subdomain in. They'd go, it'd visit those, and so on and whatnot. And then I also ran 3 tunnels through the system at the same time, iodine DNS to TCP and TCP over DNS. So this is what it looks like when I clicked on one of the simulated users. And you can see everything that shows up in green is something that matched very well. So both the rank and frequency are matching pretty well on most of those. White and yellow are a little less of a match, and anything red is bad. Now when I go down and click on one of the tunnels, you can see immediately both the rank and frequency are absolutely terrible in all of these. And in this case, all the simulated users came in between an 81% and a 60% match, whereas all three tunnels were between 43 and 35% match, which was really pretty significant. You can see over on the right, switching back and forth, the red line showing how the characters matched up with each other. You can just tell a huge difference there. And it's even more pronounced once you look at the chart of frequency versus rank. You can see all three of the tunnels immediately shot down to the bottom and stuck out like a sore thumb. So this actually gave me a lot of hope for this actually being a pretty interesting method of detecting DNS tunnels, assuming the low-hanging fruit methods didn't work. If they ever were to go back and actually fix those and make it to where they actually did use very short subdomains and were a lot more covert about it, then this may be a backup method that would be able to detect that type of thing. All right, now I'm going to start talking about the passive side of things, what I've been working on recently with PSUDP. And essentially what I'm calling it is exploiting the slack space. This is what the domain label format looks like in a DNS packet. When you have a domain, like in this case www.example.com, the dots aren't actually placed somewhere in the packet. What you have is each of the labels separated by the length, before each label is the length of that label, specified in 8 bits. So before www you have a 3, then you have a 7 for example, a 3 for com, and then each domain is ended with a 0 length 8-bit segment. And as I mentioned, you can have several answers resource records in a packet, which means you're going to have to list the same domain over and over again. Well, DNS came up with what's called a compressed form, which is actually, it's optional. It can be used or it cannot be used. Resolvers have to be able to handle both ways. But what it can do is instead of listing the same domain or even part of a domain, for instance, if later on in the packet we want to refer to example.com, not www.example.com, you can actually just create a pointer instead of putting one of those length segments in there and point back to any point in the packet previously. So in this case, we're pointing back to the 7 and saying we just want from that point on. So we want the example.com portion. So this allows the packets to fit a little more information. It compresses them a little bit. And this will be important for a technique we look at here in a little bit. Okay, the DNS protocol does not specify a length anywhere in it, and for the most part, it's if you're given what the answer is, it's ambiguous what the length would have been because there are so many valid ways of forming it. You can use compressed form, you can not use compressed form, you can only use compressed form in a couple places but not others. You can do whatever you want with it. So for length information, you generally have to look at the IP or UDP layer. So the first question I started asking is why not just modify the IP or UDP lengths and use that slack space as a storage channel? In that case, you'd be able to store binary data instead of characters, which gives you, which lets you fit more characters in there. And generally, for the most part, security tools do not analyze the slack space. So this is a basic idea of what I'm talking about here. You have your IP header, UDP header, DNS header, then you have your DNS data. Well, what you can do is you can just take the IP and UDP lengths and increase those by the amount of injected data you want to throw in that particular packet. And then you're going to have to recheck some, put a new UDP checksum on there and a new IP checksum on there when you modify it. But essentially you can put however long of a covert channel on the end of this you want, and you can put any type of data in there. It doesn't have to be formatted in any specific way. And this will actually exist going through the network until it hits a DNS resolver at some point. Now there's actually a way of creating this slack space in the middle of a DNS packet instead of just